Hello, this is module 32 of the course on application of spectroscopic methods in molecular structure determination. This is problem solving session number 4. We use the data from the infrared spectrum, mass spectrometry, proton NMR and carbon 13 NMR spectroscopy data for structural elucidation of certain simple organic compounds in this problem solving session. This is problem number 9. Up to 8 problems we have solved in the earlier modules. The molecular formula of this compound is given as C11H12O. From the molecular formula, we calculate the degree of unsaturation or the double bond equivalence to be 6 in this particular case. So this could very well be an aromatic compound because of the large degree of unsaturation that is present. Because of the presence of oxygen, let us look at the presence of or absence of OH, carbonyl stretching frequency and aromatic stretching frequency in the infrared spectrum of this compound. This is the infrared spectrum of this compound. The peak around 1708 is a very intense peak. This could be because of an aldehyde or a ketone. Typically a 6-membered cyclic ketone or an alpha beta unsaturated 5-membered ketone will come in the region between 1700 and 1710. For example, cyclohexanone has the carbonyl stretching frequency around 1710 or so. Indanone, which is a fused bicyclic system, is coming around 1705 or so in the carbonyl stretching frequency. This is an alpha beta unsaturated system, whereas this is a saturated system. So one need to distinguish whether it is because of a saturated 6-membered ring or an unsaturated 5-membered ring. As we proceed, we have to see this particular peak. The peak around 1600 might be because of C double bond C, which may be due to aromatic in this particular case. This is the mass spectrum of this compound. The mass spectrum is of limited use in this problem because not much fragmentation is seen here. The molecular ion peak is seen at m by z value 160 and loss of 15 mass unit gives the 145 peak m by z 145. The loss is because of the loss of a methyl group which corresponds to 15 mass unit. Beyond that we don't get much of an information. These are all because of water molecules or carbon monoxide, carbon dioxide kind of molecules which are in the atmosphere in this particular case. So let us find out from the NMR spectrum what information that we can get. This is the NMR spectrum of the compound. Right away one sees the D2O exchangeable hydrogen, but this is not an ordinary D2O exchangeable hydrogen. The D2O exchange happens only after a prolonged treatment with D2O containing traces of either an acid which is DCl or a base which is sodium hydroxide D. That means there is a enolizable hydrogen in this molecule. This is not because of a OH in the case of alcohol or phenol or a carboxylic acid kind of a functional group. This is a functional group mainly because of the enolizable kind of a hydrogen that is present in the system. Now before we go into that, let us look at the aromatic region. The aromatic region is a non-descriptive multiplet is what is seen. So one cannot figure out from the aromatic signals whether it is a ortho-substituted, para-substituted or meta-substituted. The only conclusion we can arrive from the aromatic pattern is because of the hydrogen intensity corresponds to 4 and the total number of hydrogens in the molecule is 12. So out of which you have to now partition this integration for 12 hydrogen. If this corresponds to 2 hydrogen intensity and this corresponds to 6 hydrogen intensity, then this would correspond to 6 hydrogen intensity and 2 hydrogen intensity. This would essentially correspond to 4 hydrogen intensity. A 4 hydrogen intensity in the aromatic region would only mean that it is a disubstituted aromatic compound, but unfortunately from the splitting pattern, which is a non-descriptive splitting pattern, we cannot tell whether it is an ortho disubstituted, meta disubstituted or para disubstituted. So the integration ratio 4:2:6 going from left to right, this multiplet is 4 hydrogen, this is 2 hydrogen and this is 6 hydrogen is what the information we can get from the proton NMR spectrum. This is a enolizable hydrogen, so it could be that it is adjacent to a carbonyl functional group. That is an important information that the NMR provides because of the D2O exchange under acidic or basic condition. So that is what is mentioned here, around 2.6 ppm. The D2O exchangeable hydrogen only under acidic or basic condition could be only because of the presence of enolizable hydrogen, like for example RCH2CO or adjacent to a carbonyl functional group. This is a enolizable hydrogen and that is readily exchanged by the presence of an acid impurity or a basic impurity in the presence of D2O. The singlet at 1.5 ppm is due to gem dimethyl group because 6 hydrogen intensity of a singlet could correspond to only a gem dimethyl group kind of a functional group in the molecule. So we have identified a CH2CO and a gem dimethyl group, and from the proton NMR spectrum we have identified that it is a disubstituted benzene derivative. So we have to put these two fragments together, but before we do that, if you take these three fragments, the degree of unsaturation only amounts to 5, but the actual degree of unsaturation is 6 in this molecule. So the sixth degree of unsaturation, or the double bond equivalence, might be actually coming from a ring which is a ring that is fused to the phenyl ring. In other words, the phenyl ring has to be an ortho-substituted derivative for this to be present. So if you put an ortho-disubstituted derivative and connect all these fragments together, it could be an indonone of this type, or it could be an indonone of this type, or it could be an indonone of this type. So the IR stretching frequency matches for these these two types of compound number 1 and 3 would match the IR spectrum, but compound number 2 will not match the IR spectrum because this is not a alpha beta unsaturated system. So one can straight away rule out compound number 2 because the CO stretching frequency here will be more than 1720 and not less than 1720, because it is a 5-membered saturated ring system. It is supposed to come around 1740 or so. Structure number 3 can be ruled out because there are no enolizable hydrogen in the molecule. Proton NMR very clearly shows that alpha hydrogens which are enolizable hydrogen. So the possible structure in this compound is correct structure is probably the structure number 1. Let us see if it is confirmed by the carbon-13 spectrum also. Structure 1, for example, has 4 types of CH carbons, which are these 4 unsubstituted CH carbon in the aromatic region, and 2 substituted quaternary C kind of a carbon, quaternary carbon. So one should see 6 carbons in the aromatic region. So what one sees is carbon number 1, 2, 3, 4, 5 and 6. There are 6 carbons very clearly seen. This region is expanded and shown between 122 and 135. The expanded region is shown here, which has the 5 carbons, 1 quaternary carbon and 4 of the CH kind of a carbon. And finally the 6th quaternary carbon comes around 162, which is because of the presence of the carbonyl functional group in this particular case. The carbonyl functional group itself comes around 206 or 207 ppm in the carbon-13 spectrum. Because it is a 5-membered cyclic ketone, it comes around 206 or so in this particular case. So the carbon-13 data is also consistent. If you look at the aliphatic region, there is a CH2, so it is a triplet in the off resonance spectrum. So this carbon corresponds to the alpha carbon to the carbonyl. Then you have a quaternary carbon, which is this particular carbon that is singlet in the off resonance spectrum. And these 2 methyl groups come as a quartet in the off resonance spectrum, coming around 30 ppm or so, 29 ppm or so for the 2 methyl groups in here. So the molecular structure is solved as this particular structure. One more check one can do after arriving at the structure. We have ruled out the possibility of structure number 2 and 3 based on the carbonyl stretching frequency as well as the non-enolizable presence of a non-enolizable carbon adjacent to the non-enolizable. There are no enolizable hydrogen in this molecule, so we ruled out structure number 3 also from the consideration. In addition to that, we can also check the CH2 hydrogen resonance. This CH2 hydrogen is actually benzylic as well as acetyl kind of a CH2. So this will essentially come more than 3.5 ppm. However, in the spectrum it comes around 2.7 or ppm or so. So this structure can be ruled out based on the NMR spectrum also. And in this particular case, this CH2 is expected to come around less than 2 ppm. But it is coming more than 2.5 ppm because this is like a toluene CH2, and that will not be more than 2 ppm or so. So the fact that it is more than 2.5 ppm rules out this structure also. Whereas this particular CH2, which is actually adjacent to a carbonyl functional group, is expected to come around 2.2, 2.5 ppm. It actually comes around 2.3 ppm or so in this particular case. Sorry, it is coming around 2.6 ppm or so. The loss of methyl group in this particular case will give a stable carbonium ion. So that is also justified in the mass spectra fragmentation pattern to give a benzyl cation from this particular structure. Let us move on to the next structure. The molecular formula is fairly complex, C6H8N2O2S. So it is a sulfur containing compound. The degree of unsaturation is 4 in this particular case. Because of the presence of nitrogen, oxygen and sulfur, we have to check for many functional group in this particular proton in the infrared spectrum of this particular compound. one has to check for NH, namely primary, secondary kind of amines or amides as the case may be, OH, SH, carbonyl functional group, carboxylic acid functional group, even sulfonic acid functional group has to be tested in the infrared spectrum. This is the infrared spectrum of this particular compound. One can very clearly see the absence of carbonyl functional group in the region between 1650 to 1700 or so. So this is not a carbonyl compound. That is confirmed because of the absence of intense carbonyl peak in this region. What you see here is essentially a C double bond C kind of a stretching frequency is the sharp singlets that you see in this particular region of 1600, not more than 1650 or so. So this cannot be because of the carbonyl functional group. What is important is the NH region. This is NH or OH we can say, because it is fact that it is sharp and it is a doublet kind of a signal, it cannot be OH. Remember, OH usually gives a very broad signal for a hydrogen bonded and very sharp signal of singlet type for the non-hydrogen bonded. The fact that you have a doublet clearly tells that NH2 groups are present in this particular system. The presence of sulfur tells us to look for S double bond O kind of a stretching frequency. 1315 and 1150 are indicated here. That is because of the symmetrical and asymmetrical stretching of the SO2 group that is being present in the system. So the infrared spectrum gives very valuable information that it has a sulfonyl group, SO2 group. It also has an NH2 group. So it could even be a sulfonamide kind of a system in this particular case. As I mentioned, the carbon-carbon double bond stretching frequency is around 1600, 1620 is the one that is seen here. Now let us move on to the mass spectrum. The mass spectrum molecular ion peak is the base peak. In other words, the molecular ion is very stable in this particular compound, and the fragmentation results in the formation of loss of 16 mass unit, which is probably due to the loss of a NH2 functional group in this particular case. NH2 would correspond to 16. We have already identified that it could be a primary amide or a primary amine, and loss of NH2 essentially, or the loss of an oxygen atom essentially gives 156 M by Z value peak in this particular case. The 92 peak actually arises from the loss of 64 mass unit from 156. In other words, if there is an SO2 loss, that would account for the formation of 92 in this particular case. The peak around 108, which is this particular peak here, could arise from the loss of SO from the 156. In other words, loss of 48 mass unit corresponding to SO would give this. Loss of 64 mass unit corresponding to SO2 will give this particular fragmentation in this particular case. So the presence of SO2 NH2 group is possible. In other words, a sulfonamide group is possible. So one has to look for the kind of exchangeable. If the sulfonamide group is here, this is an exchangeable hydrogen. So one can look for an exchangeable hydrogen in the proton NMR spectrum. Proton NMR spectrum is very pretty in the sense that this feature essentially tells you that it is a para-disubstituted derivative. There are 8 hydrogens present of each 2 hydrogen intensity. In other words, this is a 2 hydrogen intensity, 2 hydrogen intensity, 2 hydrogen intensity, and 2 hydrogen intensity. So all the 8 hydrogens are taken care of in the molecular formula. The aromatic pattern is a very typical para-disubstituted pattern. One of the substituent might be NH2, because this is a low delta value around 6.8 or so. It might be because of the presence of an NH2, which is an electron donating functional group in the aromatic ring, which increases the electron density in the aromatic ring. And the other group might be SO2 NH2, which is electron withdrawing functional group, so it comes more than 7.5 ppm or so. So the NH2 and SO2 NH2, in other words, the sulfonamide group and the primary amine group are exchangeable to varying degree by D2A exchange. The NH2 group will exchange very slowly, so this is probably due to the NH2 group. The sulfonamide group will exchange more rapidly, and this is probably due to the sulfonamide group. This is a solvent peak. In this particular spectrum, acetone D6 is used as a solvent. It is mentioned here on the top left hand corner. Acetone D6 is the solvent that is used for the proton NMR spectrum. So this is a residual solvent peak, which is because of acetone D5 kind of a molecule, which gives a multiple at around 2 ppm corresponding to the acetone signal. So one comes to the conclusion that it is a phenyl C6H4 disubstituted aromatic, para-disubstituted aromatic derivative. NH2 is present, SO2 NH2 is present. If you put all these 3 units together, one gets the para-aminobenzene sulfonamide as the structure. It fits the NMR spectral data. The aromatic region is nicely seen as a AA prime BB prime pattern which is this particular pattern. The sulfanilamide group and the amino groups are very clearly seen also in the NMR spectrum. The carbon 13 spectrum can be easily assigned. Carbon 1 is this particular carbon will be having the highest delta value because of the electron donating nature of the the electron withdrawing nature of the NH2. The nitrogen, which is electronegative, will deplete the electron density at the ipso carbon. However, in the ortho carbon, it will increase the electron density, so that comes at the lowest delta value. Finally, this ipso carbon, which is coming around 140 or so. So the two ipso carbons are very clearly seen as low intensity signal, and the two CH carbons are seen as high intensity signal, which also appear as doublet in the off resonance spectrum of this particular compound. Interestingly, the carbon 13 spectrum is recorded in a mixture of D2O and DCl. In other words, it is measured in an aqueous acidic solution in the spectrum. Let's come to the last problem in this particular module. This is molecular formula C6H10O4. Degree of unsaturation is 2, so it implies it is a non-aromatic compound. It cannot be an aromatic compound. Check for oxygen containing functional groups such as OH and CO in the infrared spectrum of this compound. Infrared spectrum is very rich in information here. There are no OH functional groups present in the system, so it cannot be a carboxylic acid, it cannot be a phenol, and it cannot be a alcohol kind of a functional group here. There is a small broadness that you see here is essentially probably due to the moisture of the sample or because of the presence of moisture in the air. This peak is seen, but if it is really an alcohol OH functional group, it will be a very broad and intense peak in this region. So one should not mistake this peak for any kind of a OH stretching frequency. This is probably due to the residual moisture in the sample or in the atmosphere. The 1760 is definitely due to a saturated ester. Saturated ester come between 1740 to 1780 or so. 1760 is very nice peak, intense peak is seen, which is due to the saturated ester for sure. There are no indications of any kind of a unsaturation. C double bond C stretch is not seen here. However, there are double bond equivalents too, which indicates that it could be a diester. In other words, because there is no C double bond C unsaturation here, the unsaturation can only be accounted for the ester functional group. C double bond O present in the ester functional group will take care of the double bond equivalence. So there must be a diester molecule in this particular system. The doublet around 1100 and the doublet around 1200 indicates symmetrical and anti-symmetrical stretching of the carbonyl CO functional group. In other words, the molecule possibly has a COO kind of a functional group. This is responsible for the symmetric and the unsymmetrical stretching frequency, which appear as a doublet corresponding to this. This is probably due to the carbonyl bending mode, and this is because of the CO single bond stretching mode of the compound that we see. The conclusion is that it is a diester of this nature, so one has to now look at the mass spec and see if further information can be obtained. The molecular ion peak is very nicely seen at M by Z value 146. The base peak at 43 tells us that it could be a acetate ester, because the intense base peak that is seen here is essentially 43 mass unit corresponds to an acetyl peak. The loss of acetate unit, 59 mass unit, is from the molecular ion peak, gives you the peak at 87. So the acetate ester is very clearly confirmed. 146 minus 59 will give 87, for example. So the conclusion is that it is a diacetate molecule. Now let us look at the proton NMR spectrum. In the proton NMR spectrum, there is a quartet. This is certainly not a olefinic or an aromatic kind of a signal, because there is no unsaturation. We have already seen in the IR spectrum of this particular compound. The 6.9 quartet essentially is because of the kind of a group which is a CH3CH kind of a group. The CH3 splits the CH into a quartet, and the CH in turn splits the CH3 into a doublet. So the coupling partner is seen here. Because it is connected to two electron withdrawing functional group, it comes at a high delta value of 6.8 or 6.9 or so. So the only heteroatom being oxygen, the only possible structure is that this has a CH3CHOR kind of a structure. The R group, of course, is an acetyl group, which is seen here in the NMR spectrum as a singlet of 6 hydrogen intensity. So this is 1 hydrogen intensity, this is 3 hydrogen intensity, and this is 6 hydrogen intensity, which takes care of the molecular, all the hydrogens present in the molecular formula. So the molecule is a diacetate of this acetaldehyde, hydrated acetaldehyde. So this is a structure of the compound. It is consistent with the degree of unsaturation, consistent with the mass spectral data, consistent also with the infrared spectrum and the proton NMR spectral data. Let us look at the carbon-13 NMR spectrum. There are 4 carbons present in the system. It is a symmetrical molecule. The 2 acetate units are symmetrical. The CH3 appears as a quartet, which is here, for example, and this CH3 also appears as an overlapping quartet. So 3 and 4 correspond to these 2 methyl groups, and signal number 2 corresponds to the CH, which is connected to 2 oxygens. So it coming around 80, 90, 85, sorry, more than 85 ppm or so. Finally, the carbonyl carbon comes around 170 ppm in this compound. So the molecular structure is elucidated based on the NMR and the mass spec. So we have seen 3 compounds here. One is an aliphatic diester compound. It is a special kind of a diester because it is a diester of acetaldehyde hydrate. And para-aminobenzene sulfanamide is the other one, and an indinone kind of a structure is elucidated based on the spectroscopic data that is provided. Thank you very much for your attention.